So we need eyes better than our eyes. Okay, you know that I told you that in the first lecture or second lecture, I told you that we, by naked eye, we can see only up to 5,000 stars in our sky, but there are far more many than that. And if you want to see fainter objects or more distant objects, you will need to use instruments. So telescopes are those instruments astronomers are using. So it's a very important fraction of the work of astronomers is to build up telescopes, taking data, so observation or experiment. In chemistry or biology, you do experiment in lab. In astronomy, you go to the telescope, or you take data from telescopes in the space. And then we spend a lot of time doing what we call data reduction. The work is to remove all the source of noise in your images, for instance, coming from other sources, coming from the atmosphere. And then once we have that, we can do analysis. So telescopes is exactly our instrumentation. We saw the past few weeks, I've described you a star map, how you can catch up and spot where the objects are. So now you have this star map, you know where the objects are. You can go in internet and look for a particular object, and it will give you the coordinates. Actually, if you go to Wikipedia and you look for a given star, Vega, it will give you the coordinates in right ascension and declination, like we described a couple of weeks ago. So armed with your coordinates in the sky, you can go and observe it. Problem is, the main part of the objects are too faint to be visible with naked eye. So they can be too faint for two reasons. The first one is they are really faint intrinsically. And the other reason is they may be bright intrinsically by nature, but they're very far away. So you can take the example, you take two light bulbs, of which both of which are 200 watts, and you put the one 1 meter to you and the other 100 meters away from you, and you will see that the amount of light you receive is different. The one that is, even so it's 200 watt bulbs, if it's 200 meters away from you, you will get less light than if it's 1 meter. On the other way, if you take a 2 watt light bulb and a 200 watt light bulb, and you put the 200 watt light bulb 1 meter and the 2 watts 10 meters away from you, you will receive more or less the same amount of light. So you can't distinguish between two things, or the object is faint because it's faint intrinsically, or the object is actually bright but very far away. So that's a problem in astronomy. I will come back on that. So now we can observe many different objects, so constellations, the first thing to do, but you can look for planets. Planets are rather easy to observe actually. You just need binoculars, you can spot it by eye. Actually, yesterday or 2 days ago, I should have put a slide on that. We had a conjunction, and you can see within one night, you can see 5 different planets. It's rare enough to be mentioned. So I think you could see Saturn, Jupiter, Mars, Venus, and Neptune during the same night in the sky. But you can observe the moon, you can observe nebulae, like the Noyon nebulae, you can observe galaxies, which are far away. So for all that, you need to be able to magnify, to observe things that are fainter or more far away. So you need a telescope. And as I just mentioned to you, when you get the light from the telescope, there are many, many things you can do more than just looking at it. You can get the total energy. You just count how much energy you receive. You can get the surface temperature, because if you have a spectroscopy, you get the black body. You can get the size. If your resolution of your telescope is good enough, you get the size. You can get the chemical composition, we just saw it. You can get the velocity relative to Earth with Doppler Shift. And you can even get rotation periods if you have several objects. So there are lots of information that gets through telescopes. So, why do you want to use telescopes? Well, the first thing is you want to see further. So you want to collect more light. So exactly like when you go fishing for shrimps, you go on the sea border, you take a net, and you just go through the water with your net to collect shrimps. If you take a bigger net, you get more shrimps than if you get a smaller net. As simple as that. Same thing with telescopes. you collect photons. So the bigger your telescope is, the more photons you get. Simple. So this is one of the first ability of telescopes. Untitled is to observe things that are very, very faint, so very, very far. But there is another thing that is very important, is increasing the resolution. That's sometimes even more important than observing fainter. So what you want to know, what you want to do is you want to be able to see details. You all know by using Googles that something that looks very blurred and not really well defined, you take your Googles and you zoom into it, you can see more details. You do that with images on your computer, you want to see a detail, you zoom into it. But your eye can't zoom like that, so telescopes can do it. So what you want to do is see better, being able to see details. So this is what we call increasing the angular resolution. So angular resolution just corresponds to how narrow you can see the detail. So low angular resolution, you will have big pixels in the sky, and high angular resolution, you have very small pixels on the sky. And that entitles us to measure radius accurately, or to be able to differentiate two things that are very close to another. So, for instance, the ability to tell that two nearby dots are distinct from one. A telescope can be 60 times better at resolving angles than a human eye. And actually, we are building up for telescopes that will be 1,000 times better than our eye. Eye is good machinery, it just works pretty well. So, for instance, this is coming from radio, but doesn't matter, it just gives you an idea. This is actually a nebulae, so it's a bubble of gas expanding. And this is the picture you get 5 years or 6 years ago with this very large array. It was a big radio telescope. Have you seen Contact, the movie with Jodie Foster? There's a movie with Jodie Foster, I don't know the name in Chinese. She's a radio astronomer, so she's working in New Mexico, and she's observing the sky, and she gets signal from aliens. You haven't seen that movie. So the movie is shot at the VLA. It's a big radio telescope in the US. So this is before the previous configuration, progression instrumentation, and this is what you get now with higher angular resolution. So you see the difference. Here you can't say anything. You see that there is probably a bit less light in the middle, so it's probably something like a shell. But when you resolve it, then you got lots of details. You see this blob here, you see all the structure of it. So resolution is very important to be able to understand what's happening. So I won't talk too much about X-ray detectors, radio detectors. They are a bit more complicated. Radio is a bit more simple, but there are very, very complex technology in action here, especially when you go to different wavelengths. We can observe in X-ray, we can observe in ultraviolet, we can observe in infrared. Those wavelengths are a bit difficult to reach, so we need to use high technology instrumentation. But visible light, the light that we use with our eye, is rather easy. Actually, we know how to do that since many, many years, since Galileo. It means 14th, 15th century. So there are two kinds of telescopes using two different properties of light. The first one is the refracting telescope, which was the first invented. So it's just using lenses, exactly like your glasses. So it's earliest telescope were refracting. So what you get is your eyes is here, you get a lens here, so the light from the star is coming over there. The lens is focusing all the light at a given point, that we call focus. And usually we put an eyepiece, another lens, smaller lens on the back to establish the order. If you have seen use loops with one single lens, you all know that if you do it away, you will see the image upside down. So actually what's happening, that let's say I have a guy here, I have my lens here. If I take the light, if I take the light coming from the guy, it's going to the focus. If I'm away from my focus point, then the guy will be upside down. Okay, so what we do, we add another lens here that will reestablish the light and reestablish. So telescopes are usually like Googles, composed of two lenses. And the other one is the reflecting telescopes that is using mirror. So it was mainly developed initially by Newton, and it took a very long time to be developed because the technology to create perfect concave mirrors is very difficult. But nowadays, all the telescopes we are using are this type. None of them are this type. So the idea is the light is coming from there, then it's reflecting on a concave mirror, then it's focusing exactly like for the lens away from it. And what you can do is, for instance, take a flat mirror that is deviating the path of light. Then the focus will be here. Instead of be there, it will be here. And then you put an eyepiece and you can use this telescope. The advantage of those telescopes is they are far more compact. Those guys have to be very big. So refracting telescope have to be very long, while thanks to the properties of mirror, you can reduce the path of light by adding several flat mirrors. So the largest currently concave mirrors are 10 meters. So a very large telescope, VLT in Chile, which is a European telescope, is composed by one 8-meter piece mirror. This is massive. We also use composite mirrors. The Keck Telescope in Hawaii is actually a 10-meter, but it's composed, small-size mirrors that are put together to make a big one. The Space Telescope, Hubble Space Telescope, is a 2-meter telescope. And we are thinking about sending an 8-meter telescope in space, which is the James Webb Space Telescope. And the next project is to build the 30-meter classes telescope. That means telescope with mirrors of 30 meters of diameter, which is massive. So there are 3 projects like that, one led by the Europeans in Chile, and 2 led by the Americans, one in Chile, one in Hawaii. So, like I said, the first telescope built were refracting telescopes, and some of them can be very big, like this one, for instance. So this one is important because it was the telescope used by Hubble to spot the galaxies and measure the distance of galaxies. However, it gives you an idea of, this is a man here, the size of this telescope. They can be 10 meters long. So they're not very practical to use, obviously. They are too big, too long. But in the old days, what you were doing with those telescopes, you were opening the dome here, so a narrow window, and you were putting the top of the telescope in that window, pointing to the object you want. And then here, you had the eyepiece, so you could look directly at your object. So for many, many, many years, that's how we were doing astronomy. Until we developed photography. So then what we did is, instead of putting your eye, it can be very tiring, you just took a photographic plate and it's collecting the photons, and it's exactly like your old-fashioned photography. It's taking pictures. And then you have those massive pictures of the sky, and you can do the study on the picture instead of spending hours in the cold ignore. Because you have to imagine that it's done usually during the night, otherwise you don't see anything. And usually it's at the top of mountains. So in the dome, during the night, it's probably 0 degrees. So I can tell you that if you have to spend 8 hours looking through this piece of glass to look for object, it's pretty tiring. So instead, you just take a picture and you bring it at home and you can work from home. It's far more comfortable. And nowadays, we're using digital cameras or CCDs instead of photographic plates, but the idea is the same. So the refracting telescope is the way it works. You have the light coming from the stars. You have the refracting or objective lens that is focusing all the light. And here you have your eyepiece, the second focus of the eyepiece, and this is where you observe it. So what is important is what we call the magnifying power. That's how big your object will look like. It's given by the ratio between the focus length of your objective lens and the focus length of your eyepiece. So it gives you what is the strength of the zoom. So when you're using a camera and you have zoom times 2, times 20, times 30, this is exactly what you are talking about. So usually, typically, you see that when you want to zoom in or zoom out, the distance between your lens and your eye is increasing. You're just moving this object in and out. So if you move this object out, you increase this, so your zoom is stronger. So it's exactly what is saying here, the focal length. If I have an eyepiece that is very thin, I will have a very long focal length. So my focus will be far further. And if I have a piece of glass that is very concave, then we have a very short focal length. You know that the width of your glass, when you're using glass, corresponds to the correction you're applying. So some of you are astigmats, or some of you are hypermetrop, or some of you are myop. Well, the shape of the lens you're using will correct different things. So if you can't see far, you will probably need a very thin lens, but if you can't see close, you will need a strong, heavy lens. So that's why in the old days, now the technology for glasses is involved, but in the old days we had people that couldn't see close, so they have those glasses that were very thick, that were making them eyes very tiny, very weird looking. Binoculars are a very simple system. So what we have done with binoculars, so it's by definition a refraction telescope. So it's using two lenses, but it's using mirror inside it to make it more compact. So you usually have two pieces. So the path of light is from your source here, is reflecting in one mirror, two mirrors, three mirrors, four mirrors, and then it's going to your eyepiece. So it's to make it more compact. Also, you want to have eyepiece to put your image in the right direction. It's good for terrestrial viewing. And usually you are not using glasses, you're using prism inside it to make more compact. Okay? So typical specs of binoculars, it can magnify up to 8 times, and the objective length here is 60 millimeter. So actually, if you're interested in observing objects directly, you don't need to go for very fancy telescope. Binoculars, you go outside with a map of the sky and binoculars, and you can already see a lot of things. A lot of things. So the main part of the astronomers, they have telescopes, typically 30 inches, and binoculars to spot on objects. So refracting telescope has the other kind with a mirror. So typically it's empty. So the starlight is going on the mirror, it's reflected, and you have several ways of doing it. The simplest way is just to put a cage here with your detector, your camera, for instance. So here it gives you the idea. This guy is inside, so he's walking on the mirror here. So this is how the telescope is, and here you have this cage here where you can put your detector, your camera, and take the picture. So the idea sometimes is to deviate, it's usually done this way, is to deviate the path of light using a secondary mirror, flat mirror. So you can do it this way, but there are many different ways you can do it. So this is what we call a prime focus. Detector is at the prime focus. This is a Newton focus. That means you put a secondary mirror here and you deviate the light at the top. You have the Cassegrain focus. That means you draw a hole into your mirror. So mirror is not full, there's a tiny hole in the middle. And then you have the secondary mirror here. So the light is doing this, reflecting here and going there. Or we have the Coude focus, which is more or less the same idea than Newton, but with two mirrors to have the eyepiece lower on the telescope. Because of course this is pointing toward the sky, so for that kind of telescope you need to be very high, to put your instrument very high. The advantage of this, it can be low. And you can imagine that actually you can have combination of those. I mean, some telescopes you have those three different configurations at the same time. So you can put three different instruments. So there are several things that we want to do with telescopes. And the first one is to collect more light than with your naked eye. So we already saw that. It's exactly like the fishing net issue. You need a bigger telescope to collect more light. The second thing is we want to see more detail. And in many occurrences, this is more important. We really want to go for very detailed study of a given object. So you need a higher resolution power. So in general, larger is better. So the aperture actually corresponds to the diameter of your primary lens or primary mirror. However, magnification, the fact that you think things bigger, is useless if you don't have the sensitivity and the resolution. So there are three things. You collect more light, so you can see things that are faint. Secondly, you increase the resolution. And thirdly, you increase the size of the object. Okay? This is magnification, the thing that you're using with the loop. But if you don't have increasing the resolution, that means that instead of seeing something like that, you're seeing something like that, Doesn't really help, right? You just increase the size of the pixel. What you want to do is be able to resolve it, go for finer grid. But if from this you go to that, it doesn't help. So magnification alone is not very useful. What you want to do is be able to increase resolution. So, parameters in the telescope is light gathering power, the ability to see faint objects, resolving power, ability to see fine details, and magnification. But once again, this is not very important. Magnification is useful for terrestrial study, but in general, in astronomy, you don't really care. What you want is to see fainter objects and have more details about it. You don't care if they look bigger. The light gathering power is directly proportionated to the size of your telescope. So this is easy to understand. This is like the fishing net. If you have a small telescope, you get less light than if you have a big telescope. So what really matters is the surface area of the primary lens, how big this thing is. So you all know that if you have a lens or a mirror that is a diameter d, the collecting area is A equals pi times d over 2 square. So this is the most important thing. You're increasing the collecting area. And the amount of photons you get is directly proportionate to A. That means it's proportionate to the diameter to the square. So if I take one telescope of 1 meter and a telescope of 2 meters, I increase the power of gathering photons by 4 with a 2 meter telescope, d to the square. And in terms of resolution, what you want to do is to be able to distinguish two things that are very close one to another. So this is rather complicated to do, actually. So for instance, here initially there are two objects, but you only see one. And you increase your resolution power, you will be able to distinguish two objects. That's the idea. The problem is, why it looks like waves? It's because light is actually a wave. And when you send light through a tiny hole, you will create this wave function. This is called the Airy function. So if I just take a tiny hole and I send light into it and I project it on the screen, if the hole is very tiny, you can do the experiment, the projected image won't look only like that, but you will have rings around it. You probably all have seen these kind of effects. It's look a bit blurred on the edges. This is an Airy effect. And actually, with our eyes, with visible light, it's very visible for tiny holes, but it's true for any even bigger apertures. So all telescopes are round. So when you look at the projected image from the telescope in your detector, it will look something like that. So it makes things even more complicated. So the telescope aperture produces fringe rings that set a limit to the resolution of the telescope. So the resolving power is the minimum angle, alpha. So you remember in astronomy we're always measuring angles on the sky. It's easier for us. So it's a minimum angle, angular distance, alpha min, between two objects that can be separated. So it's depending on the wavelength of the light you look at and the diameter of your telescope. So it's actually alpha min equals 1.22 lambda over d. D being the diameter of your telescope and lambda being the wavelength of the light you look at. So this is a function of the wavelength. So for optical wavelengths, that means the wavelength you use with your eyes, at let's say 450 nanometer, this gives alpha means equal 11.6 arc second of arc of the sky, divided by the diameter of your telescope. So remember arc seconds is that if I look the sky, so I'm here, this is the sky, and actually I'm looking distance between two objects. We measure an angle alpha. So what we do usually is you divide this into up to 90 degrees, and 1 degree we are divided in 60 arc minutes, and 1 arc minutes divided in 60 arc second. So in astronomy we usually measure things in arc second, that actually 1 arc second corresponds to 1 over 3,600 degrees. Don't ask me why. This is historical. This is the way we're doing it now. So you will see arcsecond very often. So if I have a telescope of 1 meter, that means 100 centimeter, my alpha mean will be 0.1 arcsecond. As I told you, sometimes magnification and collecting power is not our primary goal. Our primary goal is to resolve, to do resolution, so to be able to see very, very fine details. And for that, we can use a trick. So there is a trick that we call interferometer. So the idea is, instead of using a very big telescope, you use many small ones. And you put them at a given distance. And you collect light, and you do interferometry. So I don't want to come to the technical details, but some of the telescopes, they are not one big piece of mirror. There are many, many different mirrors widely separated. And actually this is very true in radio, because we know how to do interferometry in radio very well. For physicists, in radio you can conserve when you record radio wavelengths, you conserve the phase. So you can do interferometry directly. While in optical we can't do that, so we have to do it online. So currently there is no telescope doing interferometry in optical. We're still hoping to do it, but in infrared and radio it's very common nowadays. So I come back to the VLA, Very Large Array. So if you haven't seen Contact, see it. It's quite a good movie actually, and you will see the VLA. VLA is composed by, I think it's 20 antennas. So it's 20 radio telescopes that are widely separated one from the other, in different configurations. So if you take 3 telescopes, you take the beam of light coming from those 3 telescopes and you combine them here in the center, and then you can get exactly the same resolution power than a telescope that is the size of this collecting area. So if I take 3 1-meter telescope and I put them at 10 meter away or 100 meter away one from the other, it's exactly like using a 100-meter telescope. Not in terms of gathering light, of course, because you don't have a big fish net, you have many small ones, but in terms of resolution, being able to see fine details. This is called interferometry. Okay? It's a bit complex, but actually it's very, very commonly used nowadays. So Taiwan, for instance, owns one telescope in Hawaii. It's called a submillimeter array, and this is an interferometer. This is this kind of telescope. So it's composed by 6 antennas, 12 antennas, and it's in Mauna Kea in Hawaii, and it belongs to Harvard and Taiwan. And the last of those 3 important things is the magnifying power. I mentioned to you, this is actually not really interesting for astronomy. It's the ability of the telescope to make the image appear bigger. So it's important when you do projection with a screen. It's important to a cinema when you go to the movie theater. But astronomers, we don't really care about that. So the magnification will depend on the ratio of the focal length of the primary mirror lens and the eyepiece, like we saw last time. And a larger magnification does not improve the resolution power. That's what I said here. You just take that picture and make it bigger, doesn't help. What you want is to be able to see the details of it. So this is not very important. So from now, what I will do is give you an example of famous telescopes that have been used and that are used today. And I start with the first one, actually developed by Galileo. So this is 2 versions of it. So this is the first version that was something like 50 centimeter long, and the second version was 3 meter long. And what Galileo, who was an Italian astronomer, what was the idea is, before he didn't invent the technology, it was already there. Actually, those long view were used in a marine. When you have a boat and 2 ships and you want to see what is on the horizon, so people were using it since centuries. But Galileo was the first that had the idea to just do that. So, instead of pointing at the horizon, he was pointing at the sky during the night. And Galileo did many discoveries just by doing this. So the first one had a 3 times magnifying power. It was not great, but 3 times is already a lot of things you can do with it. So first thing he saw that there are craters and mountains on the surface of the moon. The moon is not smooth, but it has mountains and craters. more or less like Earth. Second thing he saw is Venus. The planet Venus has phases like our moon. You can see the crescent of Venus due to the illumination of the sun. And the fourth thing he saw is that Saturnus have ears. So actually, it's a funny story, but all know Saturn. Saturn is very famous because it has a very nice system of rings. Okay? But if you don't resolve it very well, here you have lots of light, here you have lots of light because of the projection effect of the system of rings, and here you have lots of light. So what actually Galileo saw the first time is this. Okay? So he was thinking that Saturn is having ears. So it looks like very common. Everybody knows more or less that nowadays, hopefully. But why it was a revolution is because at this time we are in the Dark Ages in Europe, and Church has the control of all the thoughts and everything in Europe at this time. And for the Church, the sky, the heaven, were immutable. That means they won't change. They'll always be the same. They will never change. And they were created by God. They were the realm of God. So it was permanent. It was always the same. And with the phase of the moon, Galileo started to have the idea. He also saw the satellite of Jupiter's. So he started to have the idea that maybe actually we're not the center of the universe. And things in the heavens are changing. And maybe actually, because the Venus has phases like the moon, so there is light turning around Venus. He saw the satellite of Jupiter, so there are things turning around Jupiter. So maybe actually Earth is not the center of the universe, but Earth is rotating the sun. So that was the conclusion of his work. He wrote a book of it, and he spent 20 years in jail. And he has been sentenced to death by the church because it was an heresy. You couldn't say that. Obviously, we are the center of the universe, not the sun. And he became blind at the end of his time in jail, which is pretty sad because he was an astronomer. So blind astronomers, they can't do much. And actually, he has been combined by a church, and he has been rehabilitated by the church in 1986. That means 400 years after being jailed. 2009 was the International Year of Astronomy, if you remember. Maybe you have seen that. It was the reason, it's because it was 400 years Galileo used the telescope for the first time. He used this telescope in 1609 for the first time. So 17th century. Okay. Then the other very famous telescope is invented by a very, 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 very clever guy. It's probably the genius of all time. So genius of the 20th century is probably Einstein, but I think the genius of all time is still Sir Isaac Newton. Newton did a lot of things, and at high school you have done physics, you hear Newton everywhere. He did optics, thermodynamics, he did mechanics, he did everything. That guy was just perfect genius. Math, he invented the integral in math. Anyway, and one of the many things he did, he decided to use mirror instead of using lenses to do a telescope. So it was his first telescope. It was very small, not big, but he was the first using a mirror here. It was built around 1670, the first, and you had to wait the 20th century to see people using it again. So he invented it, and 300 years after, we decided, probably it's a good idea, actually. And nowadays, all the telescopes used professionally by astronomers are this kind. And actually, the main part of the amateur astronomers are using gas giant telescope as well. We actually have two telescopes here on the top of the building B. There is a dome there, and there are a couple of telescopes. So once a year, the Department of Science here and Astronomy is opening the dome. So we have one night, usually in October, November. So if you are interested, so it's after the semester, but if you're interested, keep an eye on our webpage, and you will have advertisement for that. You can go there and see the telescopes with the students. There is also a refracting telescope on the top of the Taipei Astronomical Museum. So when we go there for the visit, you can go up on the roof and see the telescope there as well. So a modern version of Newton telescope is this. This is the Keck Telescope. So we have an actual picture I took myself when I was there. So it's actually a 2-dome. So it's 10 meters. The idea initially was to try to do interferometry in optical. So it's an optical telescope. So that's why they are close one to the other. The idea was to use it exactly like we're doing in radio. So having collecting light here, and then somewhere here doing interferometry. We never managed to do it. So the technology is still not there. So this is how it is. I have two telescopes, 2 mirrors, 10 meters. And as you can see here, it's not one monolithic meter. It's actually several dozens of hexagonals, 1 meter mirrors that are assembled like a puzzle together to make it one big piece. So typically, it's not the case anymore. But we used to go there, up there, and we don't have to go to the dome anymore. So here you have cameras. So you have the primary mirror here, secondary mirror on the cage here, and then you can see the hole. So the light is going through it, and under it, on the basement, you have the light conducted by usually optical fibers, or sometimes the detector is just below the mirror, and you're just taking pictures. So then, people are in the offices here, so it's warm, it's pretty good, and you receive directly the image coming from the telescope, and you can do processing and change operating the telescope from there. And even nowadays, it's even further from here. We don't even go up there. The problem is the Mauna Kea here. You had 14,000 feet or 4,200 meters of altitude. So you have 25% less of oxygen. So it's freezing cold and you're stupid because your brain doesn't get oxygen anymore. I can tell you you're very dumb when you're doing big mistakes. And you get very nervous, and it's very dry because that's why we built up a telescope there. So there's barely any water. Or from time to time we have snow, but it's very rare. Usually it's very dry, so your nose is bleeding all the time. It's a mess. So it looks very romantic to go to the summit, but I can tell you when you have to do 1 week up there, you're not very happy. So now there's all observations are conducting from the ground. So all the images are going through the internet, and you can actually, not this one, but some telescope, I can control them from my office nowadays. I don't even have to go there anymore. For instance, this is the case of this one, VLT, which is a European telescope. It's on the top of Cerro Paranal in Chile, in the desert of Atacama, so almost at the frontier of Colombia. So I've been there once as well. It's 4 8-meter telescopes. It's big. And the idea was the same, trying to do interferometry. We still can't do it, but we have lots of instrumentation, new instrumentation going there. And the main part of the project I'm involved in are using one of those 2 telescopes nowadays. And this is, for instance, a project. So of course it doesn't exist yet. This one is called the Easel Extremely Large Telescope. Extreme because the size of the mirror is 40 meters. So we are going a factor 4. And to give you an idea of how big it is, here, these are cars. Okay? So those things are massive. So this one will be built in Chile. And there is an American version of it, 30 meter, TMT, that will be built in Hawaii. And actually, Taiwan probably will be involved in the TMT. So we're going for big things. Of course, those things are extremely expensive. Typically, it costs $8 billion US, $10 billion US. So we can't do it with one single country. So usually it involves international collaborations. So the ELT involves all the European countries. The TMT involves US, Canada, China, India, and maybe Taiwan. This one is very famous. I'm pretty sure you all heard about the Hubble Space Telescope. So this was the first telescope sent above the atmosphere. Optical telescopes sent above the atmosphere in the 90s. It totally changed our ways of doing astronomy. Tell you in a minute why it's interesting to go above the atmosphere. But this one is a 2-meter telescope, and the main part of the picture, beautiful picture you see on TV, on magazines about galaxies and the universe, are coming from this single telescope. It's a wonderful piece of technology. And the story of the Hubble telescope is that when it was launched for the first time in the 90s and get up there, he was myope. He couldn't see anything. He needed glasses. So they had to prepare a mission with the space shuttle and send astronauts there to repair it. It was a pretty funny story. The first time we tried to use the Hubble Space Telescope, we couldn't see anything. And we had to send astronauts there to repair it and make it visible again. And so far we had 5 or 6 different servicing missions, so sending astronauts and installing new instruments, updating the instrumentation of the Hubble Space Telescope. So it's functioning pretty well in the past almost more than 20 years now. And we are thinking about building up a successor called the James Webb Space Telescope. So this one is a 2-meter mirror. So we are planning to build an 8-meter mirror and send. So it's an international collaboration. Almost all the countries in the world are involved in it. And last year almost have been cancelled by the American administration because of budget cuts, but thankfully it will survive it. And its launch is planned for 2018. So when I started my PhD more than a decade ago, it was planned for 2005, something like that. It's 2018 now, but we'll see. So what do we do when we do astronomy? And there are 2 main things, coming from two things I described already today. First is imaging. It's basically just taking a picture. So you want to increase the resolution to be able to see details, but it's just taking a picture. So usually the pictures are in black and white. Actually, it's what we call monochromatic. We are putting filters. So exactly like you have sunglasses, you know, they have those pink sunglasses or blue sunglasses that you can see light in blue or green or pink. Well, we're doing the same in astronomy. We're narrowing down our observations to a given range of wavelengths. So we are using lots of filters. And the other way is to do spectroscopy. So the reason why we want to do spectroscopy, it's exactly what I described earlier today, because we want to get absorption and emission line. So to be able to get more information of the object, measuring Doppler Shift, etc. So what we need to do is the diffraction grating. That means sending the light through a prism and having the rainbow color of it. And once again, what we want to be able is to have what we call spectral resolution. So instead of having spatial resolution, that means to be able to distinguish one object close to the other, in spectroscopy we want to be able to distinguish 2 different lines. If you remember the spectrum of the sun I showed you, there are many lines, and sometimes they are so close one to the other they are very crowded. So what we want to do is to be able to distinguish those different lines to really establish what elements compose the different objects. So imaging is using mainly this kind of devices. CCD, you are extremely familiar with it. You all have that. Well, this is a CCD. So all the digital cameras are exactly the same cameras, a bit less sophisticated than the cameras we're using in astronomy. Actually, if astronomers in the 80s didn't push for the development of that technology, we probably won't have digital cameras in our phone yet. So it's a combined effort from the army and the astronomers to develop this kind of technology. I make a point here, which is rather important, is that it was 20 years ago. So fundamental physics, fundamental science in general, are drivers for technology. So if you want to do particle physics, go to explore the core of the atoms, or go to explore the limits of the space out there, you need to develop very good technology. And usually this is the kind of drivers that is bringing new technology. If you rely only on applied physics, nothing new happens. You just take the same thing and make it working a bit better. What fundamental sciences are bringing to general public is development of new technologies, something that are rather totally different new, bringing new devices and that can be spread many years after to the general public. So there's a lag of 20-30 years. So some of you may be politics and in government works later, or being president of Taiwan. Please, I beg you, never forget that. Fundamental science are drivers for any devices, for technology, and anything we will use on a day-to-day life. Never forget that. I say that because where I'm from, in Europe, people forget about that, and now there's less and less money for us to do fundamental science in Europe, which is pretty sad. That means that in 20, 30 years, probably there won't be any new technology developed. Okay, so nowadays those CCD cameras are composed of billions of pixels. Billions, yeah, minimum, billions of pixels. You have millions of pixels in your iPhone or smartphone. Our CCDs in telescopes are billions of pixels. And before we used to use film, photography, but CCDs are far superior to films. For a very long time, photography was better accuracy. The details, the resolution of a photographic plate was better than the resolution of a CCD. But the advantage of the CCD is it's more sensitive to light. So you can see very, very faint objects. And the advantage of CCDs compared to photography is we have a wider range of wavelengths that can be observed with CCDs. So talking about wavelength, well, spectroscopy. So the idea is rather simple. You take the light coming from your telescope, you throw it into a prism or grism, and then you get the rainbow. That's as simple as that. And from that you can observe spectral lines. An example here, you have a stellar spectrum with absorption here, 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 etc. And you compare with a spectrum coming from the laboratory of given elements. And you can see that this line is matching with this one, 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 etc. So you can know exactly what elements are inside the spectrum. Because of the Doppler shift, things are moving away from us. Okay? So when you have an emission line or an absorption line, which is coming from an object that is moving away from us, like I said, this line will be shifted in the red compared to what it is in the lab. And this is rather important for extragalactic astronomy, to study galaxies. Because we know that those galaxies are all moving away from us, and the further they are, the faster they are moving. There is a direct relationship called the Hubble law between how far a galaxy is and how fast it's moving. So v, velocity, is directly proportionated to the distance. So if we are able to determine the velocity, that means using the Doppler shift, how much the spectral line is shifted compared to the lab, then we have an idea of the distance. So for people like me doing extragalactic astronomy, spectroscopy gives us the distance of the object. I'll come back on that when we talk about galaxies. But it is an important property. I will discuss now about the atmosphere. So we'll come back probably next week when we talk about the Earth. We'll come back on the description of the atmosphere. So atmosphere is a very good thing for us. Protects us from UV. It contains all the gas we need to breathe, like oxygen, hydrogen. It contains water, etc. So it's pretty a good thing for us. But for astronomers and astronomy in general, atmosphere is a pain. We don't like the atmosphere. The reason why is because atmosphere first is transmitting light pollution. So if you take a picture of the Earth coming from the sky, from satellite during the night, that's what you get. You see Europe here, Taiwan is there, US here, Japan, okay? You have Sao Paulo over there, India, okay, the Cape is here, for instance, Sydney, all right. So what you see is that all this light is coming from, of course, the lighting of the streets and the houses. And for astronomers, it's bad news, because if I use my telescope in that room right now, I can't see anything because I have all the light coming from all the bulbs around us. And the atmosphere has this tendency to diffuse this light. So we have kind of diffuse halos there, and we can't use our telescopes. So you basically can't use anymore your telescope in Europe at all. You have to avoid the western US and eastern US. Africa looks pretty good. Actually, there are telescopes in South Africa. Chile around there looks pretty dark. Australia looks pretty dark. But that's it. We have more and more limited places on Earth where we can put our telescopes. But atmosphere has another problem, creating another problems. And if you, however, have stared at night, gaze stars during the nights, you all have seen this property of the stars. They are blinking at us. They don't stay still light, they look like they're blinking, they're changing intensities. And it's not coming from the star. Stars are emitting always the same amount of light. It's because of the properties of the atmosphere. What's happening is that the path for the light going through the atmosphere is changing with time. The amount of air that we're having above us is changing all the time. It's due to winds, due to presence of water. So when you have a lot of water, you have more thick air, etc. Pressure. So these properties of the atmosphere are making the path of light changing a lot throughout the atmosphere. So what's happening is that your stars are blinking. Looks like they're blinking. And it's really a problem for us, because if you take a picture of a few seconds, instead of having a source which is a point, you're integrating all those blinking, and you get something that is extended. Instead of having a point source, your star being a point source in the sky, when you take your telescope and point at it, you have something that is a bit bigger. This is what we call the seeing effect. The effect that the light of the star is changing this way due to the atmosphere. So it's playing against increasing our resolution. We can't see details anymore. So that's a big problem. That's why we're using space telescopes. We put the telescope like Hubble above the atmosphere, and then you have an incredible resolution. You don't have to deal with this seeing effect anymore. So that's why Hubble produced such wonderful images, because it didn't have the atmosphere to absorb and change the path of light constantly. It was just looking straight to the object. We can use technology from the ground. So there are a very complex method called adaptive optics that is actually changing the mirror. So you have your primary mirror, and you deform slightly your mirror in real time with the change of the atmosphere. It's a very complex way of doing that. And there is a third reason why atmosphere is the pain. It's because atmosphere is absorbing some wavelengths. So you all know that the ozone layer, you heard that 20 years ago, the ozone layer is protecting us from UV, very hard UV. So if we don't have O3, ozone layer above us, on the upper atmosphere, then all the very hard UV photons will go through it and we create skin cancer, because they are very energetic. So it's pretty good for our skin, but it's pretty bad for astronomy, because that means that you can't observe UV light coming from stars. So this is just a sketch showing you the sea level and the altitude in the atmosphere with the spectrum in terms of wavelengths from gamma ray, X-ray, ultraviolet, visible, infrared, and radio. And the length of those black arrows tells you where the absorption is stopped. So basically, if you want to observe in gamma ray, you have to go above this line, above this line here, this limit of 10 kilometers. So if you want to observe gamma rays, you need to send balloons, for instance, up to above 10 kilometers, or satellites. If you want to observe X-rays, you have to send rockets above 100 kilometers, or satellites. But visible light, we know that, you can observe directly from the ground. I can see you, so that means that visible light is going through it. So visible light can be observed from the ground. Then infrared, near infrared is still okay. Infrared, you will have to go in planes, for instance, or balloons above 10 kilometers. And then radio is transparent again. So you can observe radio from the ground. So typically, from the ground, we can only observe invisible, near infrared, and radio. All the other wavelengths are not accessible for us. So we need to use balloons, rockets, or nowadays satellites. So that's why we have a collection of satellites in orbiting, used for astronomy, orbiting the Earth. Swift and integral observing gamma ray, Chandra and XMM and X-ray, Hubble, but for the previous reason I told you, for problem of resolution, Spitzer and WMAP in the infrared. So this is the sketch telling you more about atmospheric effect. So what happens is that you have parallel rays of light coming from a distant star, and what's happened is once the rays are going through the atmosphere, the rays are deflected slightly as they pass through the Earth, turbulent atmosphere, and this deflection is changing all the time. So what happened is, instead of having one single point here at the center which is the actual size of your star, due to this different deflection, due to the different width of the atmosphere above us, the position will change. Okay, it's deflected, so the position would change slightly. So instead of, and it's at the term of the 8th of microseconds. So after 1 second of exposure, or 10 seconds of exposure, instead of having one point like that, you have a halo, because the point is just changing all the time like that. So this is the seeing effect, and typically from the ground, very good seeing is 1 arcsecond. So from the top of a Mauna Kea, when I say I have a good seeing, that means I have one arcsecond. I mean, instead of having 1 point, I have a halo of 1 arcsecond, which is quite big actually. So it's a problem. Hubble Space Telescope, the resolution is 0.05. So it's 5% of this. Just to give you an idea, you observe a galaxy here from optical. In the left part, it's taken with a bad seeing. That means it's above 1 arcsecond. And the right part, it's taken with a good seeing, below 1 arcsecond. And you see that the resolution power increases a lot. Here you barely can see details, while here you can see all the structures here. So this is a very annoying effect for us. So what we can do is using adaptive optics to be able to do the resolution. So it's actually very intensive technology behind that. It's computer control mirrors. So your mirror, instead of not moving, you're slightly deforming it to correct from the change of seeing in the atmosphere. So it's pretty advanced technology. So you adjust the mirror surface to compensate for the distortion of the atmosphere. So for instance, this is an example from the Keck. So this is what you see if you don't have adaptive optics with 1 arcsecond seeing. So you don't see anything. And this is when you switch on the adaptive optics. Then suddenly from this picture you get that. You can resolve and see the 2 stars. So this is 1 arcsecond of arc. There are many different ways of doing that. I don't want to come too much into details, but this is typically how adaptive optics can work. So the idea is that you get the light from a given star that you know, or sometimes we're using fake stars. And it's a laser star. You point a laser beam to upper atmosphere, and you observe this laser beam. You know exactly the wavelength. You know exactly the intensity. So you can measure how much the thickness of atmosphere is changing. Imagine you have a star or a laser star that is above the atmosphere, very high. So you know how much, you can immediately control how much layer of atmosphere you have between the star and yourself and correct for it. So we are moving wave fronts and we deform the mirror. So the wave fronts here is deformed and due to the seeing effect. And then you deform slightly the mirror to correct for it and have a flat image. That's the idea. So it's use computers. If you want more details, we can discuss about it. So, what are the best ways for a telescope? Obviously, you want to be away from source of light. So this is a map of the US with source of light, different cities you can see. And typically, you want to be in places where it's dark. There are lots of telescopes around there, in New Mexico. Some over there. The reason why is because it's dark. Or you can do like me and go twice a year to Hawaii. It's pretty good. So this is what we're doing in Hawaii usually. So this is the Anamama Bay in nearby Honolulu. This is a natural reserve for fish. So I took the picture. So it's a creek. So it's protected. You have to pay to enter it. And so you have palm trees and sand beach. The good thing is here you have a reef, so a coral barrel. And between this and this, you have billions of fishes, colorful fishes, very nice, and sea turtles. So that's a nice place to go. But of course, I can't reconvince our government to pay me to go there twice a year just for having a good time. So usually I'm going there, spending main part of my time there. So this is me in front of the Subaru telescope is Japanese and the Keck here during the sunset. So I'm wearing a heavy jacket because you can tell you it's freezing cold up there. So always funny when you prepare everyone in the plane is preparing to go to Hawaii. They just take bikinis and bathing suits and that's it, or Hawaiian shirts, something very light. You have to take jackets, socks, heavy shoes, etc. because it's pretty cold in there. And so this is a view from the summit again. So you see that you are above the clouds. That's what you want to be able to observe the main part of the time. And the altitude is very high. So the air is very dry, so you have less variation of seeing. So the seeing is usually better when you go very high. You have less atmosphere. And this is another place where I've been to, Chile. So this is me on the top of the Easel 3.6 meter. So actually I was there to use this telescope here, the NTT. So this is in the middle of the desert in Chile. The altitude is a bit less. It's 2,800. That's why I don't need to wear an overcoat. I just can go in a t-shirt there. So typically you spend 1 week in that kind of locations. So there's nothing. You can't look for a bar. The first you can't drink. No alcohol because it's too high, so you get drunk very easily. And yeah, there's no 7-Eleven. If you want to snack in the middle of the night, you can't. It's probably 2,000 kilometers away from it. The last part, I would go very fast through it, but this is all the other wavelengths. So I talked a lot about optical, and I told you the reason why is because technology is very well understood, and it's a very old technology actually. But of course we want to be able to observe our objects in all the wavelengths possible, because each different wavelengths correspond to different properties of the matter inside it. So in radio, infrared, UV, X-ray, gamma ray, on top of optical. And just to give you a sense why, this is an example of the Milky Way. So you all know the Milky Way. This is our galaxy where we're living in. And this is different pictures of the whole Milky Way, coming from combined south and north. So the galactic center is around there. This is from the southern hemisphere. And these are different observations in different wavelengths. So typically, this is the one you're used to, it's in optical. So if you go to southern hemisphere, you will see that actually there are lots of clouds. There are lots of dust in our Milky Way. And the dust is not very good thing for astronomer, because dust is absorbing light. So if there are lots of dust, you go to a desert and there's lots of wind, lots of dust, you can't see through it. It's like fog. So it's absorbing light and we can't see through it. But if you observe the Milky Way in the infrared, for instance, you go through the dust. You can see through the dust. So you can have a totally different picture of the Milky Way here. If you observe in X-ray, you see that, for instance, there is a very bright patch here. You can see it. Because X-ray is actually very sensitive to very hot gas. So it tells us, for instance, the Milky Way where supernovae, which are big stars that are exploding, are. And gamma rays are doing the same thing. And if you go in the other way around to the radio, you will see that in radio you have all those things here on the disk that you can't see in optical or in infrared. Why? It's because radio is very sensitive to gas or molecular gas or hydrogen, and there's lots of hydrogen in the disk. So just to tell you that we can't focus only on optical. We really need to spread the whole wavelength range to really understand what's happening in the galaxy and in stars in general. So just before finishing, just jump on that. So we have many telescopes doing that. This one is very famous. It's the Arecibo Radio Telescope. In one of the James Bond movies, they filmed this thing. I can't remember which one it is. It's massive. It's in Puerto Rico. It's 100 meters wide. It's a radio telescope. Extremely big. So just to give you, this is the detector. It's spanning 100 meters of altitude. We have radio telescope. This one is the VLA I mentioned. So if you see contact with Jodie Foster, this is where she's standing. It's an interferometer. You see it's composed by many different antennas. And we can go even bigger. So this is what we call the VLBI, very long baseline interferometer. So here you have the VLA, but you can think using the globe, the whole Earth as a telescope. So you put telescope in Australia, in South Africa, this is where the VLA is, this is Hawaii, this is Europe. You can even have one in the space, and doing interferometry directly, and then you have a telescope that is 6,000 kilometers wide. It's pretty good. Infrared, I did a lot of infrared space, and this is the Spitzer Space Telescope, and ultraviolet. We have space telescope in ultraviolet, Chandra, and gamma ray observatories. For the past 3 weeks, we have discussed about how to look for your stars, your object in the sky, and telescopes and properties of light. So we'll all use this knowledge from next week and on when we start doing proper astronomy. So next week we'll talk about the Earth, and then we go away from us. Thank you very much for your attention.